So let's now describe the dynamic programming algorithm, which will take a PCFG in Chomsky normal form and also a sentence S, so some sentence like the dog saw the cat. So those are going to be the two inputs to the algorithm, and it's going to return the highest score for highest probability for any tree under the grammar. So for now I'll focus on this problem. This is the problem of simply computing the highest probability for any tree under the grammar for this particular sentence. Remember, T of S is the set of possible parsed trees from our input sentence. Of course, what we really want to calculate is the argmax, which is the tree that actually achieves this max. We'll come back to that later though. First we'll just consider this problem of computing the maximum probability for any tree. Okay, so I'm going to use n to refer to the number of words in the sentence. I'll refer to wi to be the ith word in the sentence, so I have w1, w2, right the way up to wn, that's the input sentence. I have capital N as the set of non-terminals in the grammar as before, and I have some start symbol S in the grammar. Okay, so we're again going to make use of dynamic programming, and I'll again use pi to refer to a dynamic programming table. And pi is going to have three indices. So x is a non-terminal. I is going to be a first index in the range 1 to up to n. And j is also going to be some value in the interval 1 to up to n. And we always have I less than or equal to j. Okay, so we only consider entries pi, ijx, where I is less than or equal to j. We'll see why just in a second. So this, and I'll give an example in a moment, but let me give the formal definition. This is going to be defined as the maximum probability of a constituent with non-terminal x spanning words I to j inclusive. Okay, so say I have some sentence w1, w2, w3, w4, w5, w6, and I look at pi of 2, 5, np. What does that correspond to? So if I think about the symbol np, there are going to be many, many different ways, potentially, that an NP can have a parse tree underneath it, which spans words 2 through 5 inclusive. Every one of those parse trees will have a probability, which is simply the product of the rule probabilities within that parse tree. And pi 25NP is going to be the highest probability for any parse tree with NP spanning those words 2 through 5. Given that definition, remember that this is our goal, is to find the highest score for any parse tree. Well, then by this definition, pi 1ns is going to be the highest scoring parse tree with s at its root spanning words 1 through n inclusive. And so if we can calculate this value, we've essentially solved the problem. So what we're going to see is that we can actually calculate these pi values very efficiently using a dynamic programming method, and critically using a recursive definition of these pi values, where we initially build up the pi values for small segments in the sentence, and we gradually get bigger and bigger until we have the pi value for the entire sentence. So again, just to re-emphasize what this definition means, here's a concrete example. So if I have 1, 2, 3, 4, 5, 6, 7, 8, let me just number the words in the sentence here. Let's say I have pi 3, 8, VP. So that means I'm going to consider all VPs which span words 3 to 8 inclusive. And in particular, there might be at least a couple of VPs here. One where the telescope is modifying saw, so the telescope is being used to see the man, and one where the man has the telescope. Those will in general correspond to two different parse trees. And pi 38 VP is going to be the highest probability for any of those different ways of reaching VP, spanning these different words. Okay, so next we're going to consider the recursive definitions for these pi values, which will actually drive the dynamic programming algorithm. Okay, so first of all, the base case of this recursion. So for any I in the range 1 to n, for any non-terminal x, I can define pi iix to simply be the parameter q of x goes to wi, where I define q of x goes to wi equals 0 if this rule is not seen in the grammar. So let me give you a concrete example. So if we have the dog laughs, for example, and I want to compute pi, it's this word 1, 2, 3, I want to compute pi of 2 to nn, this is going to be the highest probability for any parse tree with nn as its root, spanning words 2 to 2 inclusive. There's only one way of doing this. There's only one possible parse tree. That is the parse tree with the single rule, nn goes to dog. And so this is going to have value of the probability of nn goes to dog. So that's a very simple case. And if there is no such rule in the grammar, we just define this to be equal to 0. Okay, reflecting the fact that the maximum probability is then 0 of any tree spanning the single word dog with nn as its root. So that's the base case of the dynamic program. The recursive definition is more involved, and I'll first give the definition, and then on the next slide I'll give an example and try to describe why this recursive definition is correct. Okay, so this is for any case where we have I in the range 1 to n and j in the range I plus 1 to n, and we have some non-terminal x. Actually, this should really be n minus 1. Sorry about that. So here we have the case where I is strictly less than j. So we have some span. For example, in this particular sentence, we might have pi of 1 to np, for example. Okay. So here's the definition. So I have a max. I'm going to have a max firstly over all the ways of rewriting x in the grammar. So this is a max over all productions of the form x goes to yz in the rule set. Remember, our grammar is in Chomsky normal form, so we can just consider rules which are binary, where we have 2 children. And then we have some variable s, which can take any value in the range I through to j minus 1. This is what will be called the split point. We'll see why shortly. And so I'm going to search over these two choices, the choice of rule and the choice of the value for s. And then I'm going to multiply in q. This is the probability for this rule that I've chosen. And then I have pi of I s y, where y is here, and pi s plus 1 j z. Z is here. And so this definition is recursive because this value of pi is calculated based on other values of pi. In particular, it's based on values of pi which are based on shorter segments. So the length from I to s, or from s plus 1 to j, is smaller than the length from I to j. Okay, so that's rather abstract. Let me give you an example illustrating why this definition is actually correct. So here's the example. Let's just number these words. And let's say, for the sake of argument, we want to calculate pi 38 VP. So that's going to be the maximum probability for any tree with VP at its root, spanning words 3 to 8 inclusive. So firstly, I'm going to write down how this definition plays out, and then we'll justify it. Let's say, for the sake of argument, I have 2 rules expanding VP in my grammar. One of them is VP goes to VT NP, and the other one is VP goes to VP prepositional phrase. Say for the sake of argument, these have probabilities 0.4 and 0.6 respectively. So I'm going to search over two different things. I'm going to search over all possible rules in the grammar, and I'm going to search over all values for this value of s, and that actually means I'm going to search over s in the range, so I is 3 in this point, 3, 4, 5, up to j minus 1, j is 8, so that's going to be up to 7. So let's go through these options. So I can compute Q of VP goes to VT NP times pi 3 VT times pi 4 8 NP. So that's one option. So I can calculate this value. So this is the case where I choose this rule here, and I choose the split point equal to 3, and so pi is is 3 VT, and pi s plus 1j is 4 8, and z is np. Another option is q vp goes to vt np times pi 3 4 vt times pi 5 8 np, and so on and so on. Finally, up to q vp goes to vt np times pi 3 7 vt times pi 8 8 np. So here I've fixed this rule and I've searched through all these values for s, and then I can do a similar thing where I have q of vp goes to vp pp times pi 3 vp times pi 4 8 prepositional phrase. So that's where I've chosen this rule, and the split point is 3, right the way through to q of vp goes to vp pp times pi of 3 7 vp times pi 8 8 prepositional phrase. Okay, so I'm going to search through all of these different possibilities. I'm going to search over all possible rule choices expanding VP, and I'm also going to search through all possible split points. So each of these products is going to have a different value, and I'll simply take my final value of pi of 3 8 VP as the max of all these different values. And as we'll see, when we actually implement this algorithm, we're going to have to be careful in terms of the order in which we calculate these pi values. We'll calculate pi values bottom up, i.e. for smaller segments before we get to larger segments, which will ensure that these pi values at lower levels are calculated before this final pi value.